Hello everyone, and welcome to the NEATEC Electronics series. This episode is about the atom, so let's get started. Alright everybody, so let's talk about the atom. Specifically, let's talk about the components of an atom. Alright, so what is an atom made of? So basically, it's made up of three things. You're going to have electrons. You're going to have protons. And you're going to have neutrons. All right, so let's do something with these. Let's kind of put them in a table, shall we? So when you take notes, this will help you. If you can arrange them right, it might help you remember better. But let's just look at it. So I put this in a one right under the other. So electrons on the top here, let's write something about them, right? Let's say the charge. What is the charge of an electron? It's negative, all right? All right, what's the charge of a proton? It's positive. And how about the neutron? There's no charge on a neutron. It's neutral, all right? So those are the three things you need to remember right now about an atom. There's three components: electrons, protons, and neutrons. Electrons are negatives, protons are positive, and neutrons, they don't have any charge. Now let's look at the location real quick. Where do you find these in the atom? Well, these, I'm going to use a term, I was going to say spinning, but these are, I'm going to say, on the outside. All right, and you'll understand that later. But the protons and the neutrons, these are both located in what's called the nucleus. Nucleus. All right, so let's talk about, let's draw an atom. That's probably the best thing. To draw this, let's take this most simple atom we have. It's the hydrogen atom. Got it? The hydrogen in the nucleus is in the center of the atom. It has one proton, right? And then spinning around the atom, you're going to have one electron. Now, how I usually draw an electron, and you're probably going to see it, is you have the letter small e with a minus sign on it. Sometimes people draw a circle around it, sometimes they don't, but that just means one electron. So I'll say one electron. Now notice, the electron has a charge, a negative charge, right? The proton has a positive charge. When the electrons equal the number of protons in the atom, this is called an electrically neutral atom, or sometimes they use the term balanced. It's electrically balanced. All right, that's because the number of electrons equal the number of protons and their charges cancel out. So we have something called the atomic number. What is the atomic number equal to? It's equal to the number of protons in the nucleus, right? Now, if the atom is electrically balanced, obviously it's also going to equal the number of the electrons, right? But you can't always count on that. But if you were given a problem and it asked you, is the atomic number equal to the number of electrons in an electrically balanced atom, you would say yes. All right? So we just drew that. You can do this exercise for different atoms, but it's basically the same. And the point I'm trying to make to you here is that when you have a balanced atom, the number of protons equals the number of electrons. And the overall charge in an electrically balanced atom is 0. Okay? All right, so there's a lot more to be discussed because these these electrons arrange themselves around the nucleus in various ways. And that's what we're going to discuss next. All right, everybody, we'll see you soon. So, at this point, we've discussed protons, neutrons, electrons. We understand what a neutral atom is and the atomic number. Now, let's talk further about how these electrons orient themselves around a nucleus, okay? And we're specifically talking about the Bohr model of the atom, all right? Remember that, Niels Bohr. Niels, there should be an N there, Niels Bohr. All right? There you have it. If you would like to look him up. Obviously, this guy was very intelligent for his time. Probably very intelligent if he was around now. But we're talking about the atom here specifically, all right? The Bohr model of the atom. Now, if you noticed, I drew an atom. It has 14 neutrons, 14 protons. So what's the atomic number of this atom? Just for the heck of it, let's just do this. Atomic number, that's going to equal what? 14. How many protons are there? 14, right? So how many electrons are we going to need for an electrically balanced atom? We're going to need 14 electrons, right? So how these 14 electrons are going to be distributed, we have things that are known as shells, right? In this case, we have shell number 1. That's this one right here. Shell 1. Okay. The next one's going to be called shell number 2. When we do that, we see it right here. Shell number 2. And finally, we're going to have shell number 3. Got it? Where's shell number 3? It's obviously right here. Got it? So there are your shells listed. Now, you can have more than 3 shells, right? You can have 4 or 5, however many shells you need to take care of all the atoms. So one thing I want to let you know is the energy of an electron. These actually represent energy levels. shell number 1 contains the lowest energy electrons. Think about it. They're the most tightly bound electron because of the attraction to the nucleus, right? As you get further away, the electrons become less tightly bound. All right? So these shells actually represent energy levels. All right? So one question you're probably going to need to know, I know you're going to need to know this, is how many electrons can we put in each shell? Well, guess what? There's an equation for that. So if we look at it, I'm going to say the number of electrons, right, is going to be equal to 2 times n squared. And n, the small n, is equal to the number of the shell. Right? So for shell number 1, n is going to equal 1, right? 2 times 1 squared is equal to 2 electrons. We're going to call this total electrons here. In shell. You know what? Instead of calling it the total number of electrons, let's make this the maximum number of electrons. What do you say? So this is the maximum number of electrons in the shell. So for this one, it's 2. How about for the second shell? What do you think it would be? Give it a try. Pause this and then restart it. We'll do it together. Okay, welcome back. So if we're doing the second shell, this is going to be what? 2 times 2 squared, because we have the second shell, right? That's going to be 2 times 4, which is equal to 8, right? All right, why don't you pause it right now and calculate the maximum number of electrons that could be located in shell number 3. And then start it back up when you have your answer. Okay, everyone, so for shell number 3, using this formula, it's simply going to be 2 times 3, because that's the third shell, squared, which is equal to 2 times 9, which is equal to what? 18, right? So the maximum number there could be 18. Remember this formula, you're going to need it, all right? Because at some point you're going to be asked how many electrons can you put in a shell, all right? So that's important to remember that. All right, so that's how you calculate the maximum number of electrons you can have in a shell. Now remember, these shells, it's important that you think of these as energy levels, right? The lowest energy shells, shell 1, 2, 3, and so on. Now, the outermost shell, in this case, we're going to fill this in, but we have 3 shells worth, or not quite 3 shells worth, but the outer shell is termed as the valence shell, all right? Electrons in this valence shell with sufficient energy can leave the atom. Obviously, it would leave the atom electrically unbalanced, but an electron that's given enough energy where it can leave that valence shell, and it's going to jump to something called the conduction band, where it's going to give the basis for electrical conductivity. All right, we're getting there. We haven't quite gotten there yet, but remember, valence shell. Let's write that down. Sometimes this is termed valence band. that's equal to the outermost shell. All right? So, now, let's think about this for a second. When you have an atom, an electrically balanced atom, and it loses an electron, it's going to lose it from its valence shell, right? It's going to go off somewhere. It's going to leave the atom electrically unbalanced, right? Because you're still going to have the same number of protons, the same number of positive charges, but instead of having 14, in this case, 14 electrons, you're only going to have 13. That means it's going to have a positive charge, right? That means it's a net positive charge, okay? So what happens if you have a valence band? We haven't talked about this too much yet, but you have a valence band and all of a sudden it gains an electron. Well, that means you're going to have another electron than you do a proton, so the net charge of the atom is going to be negative. All right? So when you hear the term ionization or an ion, ionization, that's like a verb. In other words, they're going to remove an electron from the outer shell. Generally, that's how I've seen it used. An ion is an atom that is not electrically neutral. All right? So that's one way to think about it. So let's talk further. By the way, I didn't write that down. I could say, let's just write the ion, and that is a non-electrically balanced atom. Okay, so it's not electrically balanced. In other words, it's either lost an electron or two, or gained an electron or two. All right, so that's what an ion is. So let's go back and talk further about the shells, shall we? So I'm going to remove these right here. I'm going to remove this right here to get some space. All right. Now, shells consist of something called orbitals. Orbitals are named the following. All right, right down here. Now the orbitals are S, P, D, and F. These are lowercase, right? The shells are usually written in lowercase, all right? So specifically, each orbital has a number of electrons, a maximum number of electrons it can hold, right? So if we come over here, the max electrons, right, in orbital, S is going to hold 2, right? The p orbital will hold 6. The d orbital will hold 10. And finally, the f orbital will hold 14. All right? S, P, D, F. Those have German names that go along with them. I don't know them, but I'm sure you can look them up in Google if you're interested in that. So remember this, I don't want to get that confused with anything. That is the letter F, all right? Okay, So, now suppose we have, well, how are we going to write this? Let's think of an example, right? And if we think of an atom, nitrogen, right? Nitrogen has an atomic number of 7. Therefore, you're going to have 7 protons. And hence you're going to have 7 electrons in an electrically balanced atom. So let's distribute these first, but let's do it in notation terms, right? So how many atoms or electrons can the first shell hold? Well, you look at this right here, we said that we can hold 2 electrons, didn't we? Okay, so how you write that, it's going to be, since it's in shell 1, you would write it here we go. So how would we write that? We're going to say this can be written as 1, okay, S2. All right. Now, and then it also is written. This is all this. It's continued. This is the second part of it. 1 at 2s2, and then 2p3. So this is your shell right here. So in shell 1, shell number. So in shell number 1, you can see over here we have a maximum of 2 electrons, right? Okay, so we have 2 electrons. Now we have to distribute those 2 electrons. Well, these are the orbitals. You can see S, it's on top. It takes 2 electrons, right? So this, that's your orbital, right? And this number right there, that's your number of electrons. Okay, I just draw E minus means electrons. Got it? That's the notation. What's this saying? So we used 2 electrons here, didn't we? Right? If we come down here to the next one, we're in the second shell. The second shell can hold a maximum of 8, right? Well, we're good, right? Because we only have 7 total we need to take care of. So obviously 2 of them are going to be consumed in the s orbital, right? We're going to have 3 left over, aren't we? How many can the p orbital hold? The p orbital can take 6. Well, the remaining 3 are just going to go in the p orbital. So you have 3 electrons right here that are in the p orbital of the second shell. Obviously that's the end. Obviously you have, for the second shell, you have in the s orbital, you have 2 electrons. All right? So that's the notation that's used to describe this kind of thing. All right? So remember, the takeaway here is you have shells in the atom. The shells represent energy levels of the electrons. Each shell can only hold a maximum number of electrons as defined by this equation right here. That's your equation to determine how many electrons can be, the maximum number of electrons that can go into each specific shell. When you know the number of electrons you need to distribute, which in this example you did, right? Then you need to know how to distribute those electrons in the shell. So obviously if you know the maximum number of electrons in shell 1 are 2, then obviously each shell consists of orbitals. The 2 are going to be consumed in the s orbital. So there that gives you your 1s2 as we described, right? You still have 5 left over. Well, then you're going to come down here to your next shell, because that's the next one to be filled, right? You can hold a maximum of 8. Okay, you only have 5 to distribute. That can hold a maximum of 8. Well, they're going to go in the second shell. How are they going to go in the second shell? Well, 2 of them are going to be consumed in the s orbital. That's what we're saying right there. Right here, right? Trying to draw that so you guys can see it right there. All right, the next one, p. The p orbital can hold 6 electrons maximum. You only have 3 left, so they're just going to go in the p orbital, right? All right, everybody. I think that pretty much tells you the key things you need to understand. Now we're going to move on. One last thing I want to go over with you, all right? They have something, in this course, there's going to be something that's discussed called the core. And I'm going to draw this one in orange. In this case, for what I've drawn here, suppose we have atoms in shell 3. So shell 3 is our valence shell, all right? So if I took the charge all the way, including up to shell 2, right up to the valence band, but not including the valence band. So if we have 14 protons here, right, and then we count the number of electrons that are in shell 1 and shell 2 in this case, but not in shell 3. In other words, all the way up until it's in this orange circle I drew. Now that's going to be what's called the core. It just simplifies things is all it does. Your core is going to have a positive charge, and it basically simplifies this because you don't have to tally up all of the electrons and everything below that. So this would have a charge of, say, depending what the atom is, suppose it's a charge of +2, your core, that means your valence shell is going to have a 2 electrons in it for an electrically neutral atom. That's all. So the core is sometimes used to help simplify the discussion of an atom for electrical purposes, all right? All right, so at this point, we've really covered quite a bit of material. I believe we're going to have one more section in this video, and we're going to talk about insulators, conductors, and semiconductors. See you soon. All right, so let's finally conclude our discussion about the atom. And to do that, we have to talk about 3 groups of materials: insulators, semiconductors, and conductors. All right. Now, those items that are termed as insulators, they do not conduct electrical current. They insulate it, right? So they're usually compounds, not single elements. They have high resistances. Obviously, a resistance is impedance to current flow, so it makes sense, right? The valence electrons are tightly bound, or more tightly bound, right? That means they cannot jump into the conduction band as easily as others, right? Examples of these compounds are rubbers, plastics, ceramics, woods, things like that, all right? Now, if we talk about semiconductors, Well, let's talk about a conductor next, right? Let's go to the other end of the spectrum. A conductor easily conducts electricity. It's usually a single element material. It usually has one valence electron very loosely bound. That means just a little bit of energy, it can jump right up to the conduction band. Examples are gold, silver, copper, metals, right? That kind of thing. Now, if we talk about semiconductors, they're neither a good conductor nor a good insulator, right? They're in the middle. They can be a single element or multi-element. So single element semiconductors have 4 valence electrons. An example of that is silicon. So remember, a valence shell of an atom represents a band of energy. Okay? So that's what I have written over here on the right. I have band, if you notice, right? This is the conduction band here, valence band here, right? It's a band of energy. The Y scale is energy. Starts off with 0 energy and gets higher, right? So valence electrons are confined to the band of the valence band, right? Valence electrons acquire energy. When they acquire enough energy and leave the valence band and become free electrons, they move to the conduction band, all right? So that's the process, what has to happen. So in this case, if we look at this one, this is an insulator, isn't it? Look how much energy has to be obtained by an electron in the valence band to jump to the conduction band. It's quite a bit, right? I mean, I can't give you an exact amount, but because there's so many different materials, but the difference in energy levels from the valence band to the conduction band are much greater than for these other materials. Now, if you look at for these other types of materials, semiconductors and conductors. Now let's look at the next one. What do you think this middle one is? This is going to be a semiconductor. All right? They have less energy, and not as much energy is required for an electron to jump from the valence band to the conduction band as for an insulator, all right? But still energy is needed. And finally, what do we have over here on the right? There's only one left. This is going to be a conductor. If you notice, there's an overlap between the conduction band and the valence band. That's what I wrote down here in words. I tried to draw it so you could see it. This is important because this means electrons in the valence band can very easily jump to the conduction band to conduct electricity. All right? Now, we have to talk about bonding. So if I draw a silicon atom, okay? Based on what we just talked about, this is your core, +4, right? And here's your valence. That's your valence shell. And it's going to have, I'm just going to keep it in black, why not? It's going to have 4 valence electrons in there. Now this whole atom is electrically neutral, because the core, which contains the protons, neutrons, and all the electrons of the shells beneath the valence shell, you're going to have a positive charge. In this case, it's +4. Well, you have to have then 4 other negative charges to make it an electrically neutral atom, so hence you have 4 right there, right? In the valence shell. So remember, these energies are farther away from the nucleus and require less energy to break free and to become free electrons, all right? So let's talk about bonding like we said. Suppose now we have another, I'm going to draw another one right here. I'm just going to call it, this one's the same atom. This is silicon, that's its designation, plus 4, right? Whenever I say silicon, it has plus 4. So why don't I do this? We're just going to call it silicon, all right? And we're going to have now another, let's move that a little bit closer, shall we? Now, what do you say if I do this? I'm going to move this electron right here. I'm just going to move it up here just a little bit, okay? Now, suppose we draw the shell, the valence around this one, okay? Now, this also has 4 electrons. I'm going to draw its electron a little bit lower over here, right? Actually, how I should draw this, if you think about it, let's take it. Just move it right in here, right? Because they're going to cross, aren't they? So we'll bring this one right here. There's the electron. It's going to come in right here. Come around. That's that one, right? So you're going to have an electron from this one, aren't you? You're going to have an electron here, an electron here, an electron here. Do you see how this atom shares 2 electrons with this one? That's called a covalent bond. We also have a covalent bond here. It's going to be 2 electrons. So you're going to have your silicon here. Guess what? You're going to have one on this side too, aren't you? So your silicon, you're going to have another electron here. And guess what? You're going to have one up here. Here's your silicon. It's going to share another electron here. And of course, all of these have their other electrons out here. And the same here. Now look, when I said we're going to talk about bonding, this is what I'm talking about right here. Silicon, the silicon lattice. You see a piece of silicon. It's shiny, it looks like glass. This is the structure, all right? It's regular. It repeats itself. So each silicon atom, basically, it has, if you think of it, has a core of plus 4, and its valence electrons, it has 4 electrons, right? And each one of those 4 electrons is shared with its neighbor. So there's 2 electrons shared with each neighbor. And hence the covalent bond, and hence you have your structure, right? Another way to draw this, silicon, 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 silicon. Yeah. There's 2 electrons, 2 electrons. These are just like minus signs. These are just like minus signs, okay? All right, everyone. Thank you for your attention, and I will see you on the next video. Thank you.